Hello everyone, my name is Se-Kwang Kim. Today, I'm going to talk about compositional generalization issues as semantic parsing, which is a natural language processing topic that I am interested in. So let's get started. Before diving into compositional generalization issues, let me introduce what is semantic parsing in terms of its definition and applications. Semantic parsing can be defined as the translations of natural language utterances into machine executable meaning representations, often called programs or logical forms. Let's take a look at this example. For a given natural language question, like how many competitions were held in 2006, we do semantic parsing for the question, resulting in a table query like parentheses open, count parentheses open, filter underscore number underscore, and so on, which is a program. By doing such semantic parsing, we can expect some advantages. Let's say the original goal was to answer the question by reasoning over the given table. If we want to directly obtain the answer from the natural language question, we need to devise methods to somehow encode tables and utterances onto a continuous space and process them in the space. Instead, if we have the program that's semantically isomorphic to the given original question, the only thing we need to do is executing the proper machine like Excel, whose reasoning process is transparent, controllable, and reliable. In other words, semantic parsing enables to leverage machines that strictly enforce given rules. Thanks to this advantage, semantic parsing has a wide range of applications. Beyond the aforementioned table query, resulting logical forms can be queries for much complex databases, as in the above example. To go further, in the context of task-oriented dialogue system, extracting the state from the user utterance via semantic parsing is vital because the state in turn is executed against API and influences the next utterance of the system. However, there is a huge bottleneck for learning semantic parsing. Data collection cost for training is extremely expensive. This is because annotating the correct logical forms for text requires human experts. Hence, it would be desirable to devise a semantic parsing method that works well even in sparse data condition. In particular, a good model must be able to handle compositionally novel test instances. What is compositionally novel instances? Let's go over text-to-SPARQL query semantic parsing task. Assume that a model has observed two questions like who edited Inception and did Guy Hamilton direct Goldfinger. We further assume that the model has never observed any example which have who and directed at the same time during the training stage. And then at the test stage, we show the instances like who directed Inception that has both who and directed. For humans, we possess an ability to handle such compositionally novel instances, as known as compositional generalization ability. Unfortunately, it has been found that current deep learning natural language processing models cannot do so. Even if we show that all atomic words during the training stage, the NLP model cannot understand the meaning of new combinations of obscene atomic words. For instance, RNA sequence-to-sequence models failed to repeatedly copy a verb jump according to the input command jump twice if the model has never repeatedly copied the verb jump during the training stage. Transformers, de facto standard NLP architectures make no difference too. So what can we do about it? what types of inductive bias do deep learning NLP models need to learn for achieving compositional generalization? And how can we instill the inductive bias to the models? To answer these questions, let's think about the semantic parsing task's unique characteristics. First, the targets of semantic parsing are logical forms, which strictly follow syntax defined by humans. For example, arithmetic expressions, which are also logical forms, obey the context-free grammar, such as operators must be placed between two terms. In some cases, we have full knowledge about the context-free grammar that generates logical forms. Second, due to the highly structured nature of logical forms, in some cases, statistical methods or manual annotations can provide high-quality source target alignment. So why don't we use them? So far, diverse lines of research have been carried out for resolving compositional generalization issues while exploiting the characteristics of semantic parsing tasks. From now on, among them, I will cover three distinct approaches for the sake of time. The first approach is adding layers or subregions for explicitly capturing or modeling relations. The second approach is leveraging pre-trained language models. The last approach is improving training dynamics of models by augmenting data or designing the training episodes, each of which can help models to learn how to handle compositional novel instances. Researchers use pre-computed or given alignments for attention mechanisms. Introducing relation embeddings at attention or giving supervision by pre-computed alignments for attention is possible. Specifically, to solve text-to-SQL tasks, the upper study applied relation-aware attention, which depends on predefined schemas that SQL query must follow. As another example, the lower study introduced masks at the dot product comparison in the attention between query and key vectors. Concretely, a hard mask, which is statistically computed in advance, opts out the alignment between two tokens that are not supposed to be aligned. Another possible way to instill pre-computed relation information is supervising the alignment. As a result, the attention supervision turned out to be effective at some compositional generalization tasks, which are program split in these tasks. However, applying pre-trained embedding enhances the score much more. Also, I applied T5 models for these tasks and obtained a competitive scores. This leads to another approach, which is leveraging the pre-trained language models. GPT, BERT, and T5 are typical pre-trained language models that everyday NLP researchers use. Note that, unlike BERT, these models can further generate sequences. As they have seen hundreds of thousands of tasks, they can quickly adapt to new tasks via fine-tuning or even via few or zero-shot setups. It turned out that pre-trained language models can show largely improved generalization scores compared to models that learn from scratch, as shown in the below. However, these pre-trained language models are huge. Hence, it is hard to deploy them in edge devices or real-time chatbot that requires high latency. Furthermore, pre-trained language models are specialized at generating natural language text rather than logical forms, which means that the structural gap between the natural language texts and logical forms needs to be addressed. As seen in the middle example, logical forms can have different semantic structure compared to natural language. The natural language question itself do not mention student ID at all, but the corresponding SQL query must contain a student ID to have the same meaning with the question. Hence, it makes sense that reducing the structural gap would induce better adaptation of pre-trained language models. To validate this idea, as shown in the bottom figure, I tried to replace queries' synthetic words with questions' natural words. Such matchings are obtained based on the mutual information across the corpus. As a result, this simple word substitution preprocessing methods enhance GPT-2 and T5's compositional generalization. The second approach is improving training dynamics. The basic idea is that deep learning models fail at compositional generalization because we have not provided instructive enough training data. To illustrate this, let's go over the zero-shot learning of repeatedly copying jump. We want models to repeatedly copy the verb jump during the test stage after showing training data that contains only few verbs, exactly 3, are repeatedly copied. What if we add more verbs other than run that are repeatedly copied during at the training stage? As shown in the right graph, as the number of distinct verbs in the training set increases, the score models achieve gets better. This shed a light on the possibility that data augmentation can induce deep learning models' compositional generalization. Based on this idea, a number of studies that leverage manual data augmentation or data-driven data augmentation have been suggested. Instead of randomly feeding training examples, what if we feed training examples in a specific order to teach models well? A recent meta-learning approach shows that it is possible to do so by designing training episodes that simulate the test condition that challenges compositionally novel instances. To this end, we consider this study consider a virtual task consisting of a meta training batch and a meta test batch. The meta training batch mimics the training stage so that we randomly sample instances to make the batch. The meta test batch mimics the test stage so that we sample instances that are compositionally distant from the meta training batch based on a kernel function that captures the string distances. After composing two batches, do the meta learning for given models. As a result, the study shows that improved scores, but it still leaves the large gap from the human level generalization. To wrap up, semantic parsing is important as it bridges neural words that is specialized for intuitive reasoning of highly complex data and symbolic word that is specialized for discrete reasoning of programs. However, learning semantic parsing requires training data annotated by experts so that tasks suffer from the data sparsity problems. In particular, the ability to handle compositionally novel instances is necessary, and making model to be equipped with the ability is not easy. Besides three approaches that I talked about, neurosymbolic approaches or knowledge distillation approaches have been suggested. If you are interested in this topic, feel free to contact me. Thank you for the attention.